So again, when they ask you to do a talk about the future of particle physics, I think that it's sort of standard to take your crystal ball and try to understand where you're going. My crystal ball, especially because a lot of people have already spoken about dark matter and the neutrino, has a big H on the middle of it. And I think that you know where I'm going. But also, I'm trying to keep us grounded. And so from time to time, I will go back to this event in 2003, where, there was a panel on the future of particle physics in which Don participated. But also you can see that some of the people who talk today talk also in this event. And many of the people that are here today, like Chris, was also part of this event and commented at this event. And this event is interesting because it was about 7 years before the start of the LHC. And now we are about 7 years before the start of the upgrade of the LHC, the high luminosity LHC. And again, I think it's good to keep an eye on where we have gone since then. And that event was the panel was chaired by Carlo Rubbia. So at that point, we had the standard model. And so we had, we knew that we had that the genetic code of the nuclear world was composed of quark and leptons. The quarks, a matter particle, were spin 1/2. We knew that the spin 1 particles, the force particles, the vector boson, were responsible for the interaction in the sun, for the weak interaction, the W, the Z, and the Z. We knew that the gluons were responsible for binding together quark to form nuclei. And we knew, of course, that the electromagnetic interaction was exchanged by the photon. And we knew that these force particles were spin 1 particle. And then we had the spin 0 particle, which was not a particle matter or a force particle. But this particle was really what was holding together the standard model. And in fact, without that particle, all the particles in the standard model will be massless and the standard model will collapse. So in a sense, in 2003, the Higgs was missing. And so we knew where we were going because we knew also that the cross-section, for example, or WW scattering will become infinite with energy without the Higgs. And so we had what was called the no-lose theorem, which I think Chris had in his pocket when he argued for the LHC. So at the LHC, we had to find the Higgs or something at that mass scale, which was a very good argument to have to build the LHC itself. So nonetheless, it took about 20 years from the original studies for the Higgs, its approval, and then to the first collision. So this project takes a long time. But it was a discovery machine covering all the possible Higgs masses between 100 times the mass of the proton to 1,000 times the mass of the proton. And it's an amazing achievement of our community. We have built the largest and most sophisticated detectors ever to study the result of the LHC. We developed tremendous magnet reaching 8 Tesla to bind together to keep the proton in this racetrack. We are operating the LHC at the highest vacuum comparable to the matter in outer space. We are reaching temperatures that are higher of the temperature of the sun. And to operate this superconducting magnet, we are operating at 1.9 Kelvin. It's really a tremendous success. Here is a picture of one of the experiment atlas where I'm working. And here you are sitting more or less in the middle, and you have like the beam pipe here, and you can see the various components. So you can see that you're using to find your particles. So you have the muon chamber out here, then you have your hadronic calorimeter, so particles that contains quark gets stopped in this calorimeter. They deposit all their energies there. Electrons and photons are going to be stopped in the electromagnetic calorimeter, and then you are going to have tracking system inside the magnets which are bending particles in order to understand their momentum. And so you can see here the signature that you will see. So only the muon will reach the muon chambers. You see here the hadronic particle, here the photons and the electrons, and the bendings that allow you to measure the momentum of charged particles. So what was said in 2003? Well, it's really quite interesting. I mean, Sheldon Glashow said, astonishing discovery which do not confirm the theory of anybody in his room. It's rather funny. Pierre de Roulin, we will find Higgses and supersymmetric particles. Carlo Rubbia, suppose we don't find the Higgs, then what? What is next? So I would say that there was a lot of people in that panel and in that room that really thought that we will discover supersymmetry and that we might not discover the Higgs boson. Again, what we found instead was that we discovered the Higgs boson, and here is just one characteristic, one of the most, of the best event where you have the Higgs boson decays into Z boson and then going to muons, which leaves you really a very, very, nice signature. And again, what we saw at the end, we saw this is a standard model background without the Higgs, and we saw a Higgs particle at 125 GeV as really a phenomenon. So now the Higgs is a bit older, is about 10 years old, and we have measured a lot of the Higgs production and decay. And down here, you can see the ratio of the production and decay with respect to the standard model. And you can see that both the production and the decay are really matching, if you want, what you are predicting in the standard model. So the Higgs is very standard model-like, but if you see also what you see here, you see that we have really measured well only the coupling of the Higgs to the W and the Z boson, and the coupling to the very massive quarks and quarks of the third generation. While instead, here is the error on the charm quark. It's enormous. We are starting to get closer to the muon. So we are really still at a very small picture of, we don't know yet a lot about the Higgs boson. Also, our understanding of the standard model rests on the assumption that electroweak symmetry breaking occurs through a scalar potential. So in the hot universe, this potential was parabolic, and the Higgs had the zero mass, zero value expectation value. As the uniform expanded and it became colder, the Higgs vacuum, the Higgs got a expectation value of 246 GeV, so it rolled to this position in this Mexican hot potential. But we don't really have any experimental evidence that this is the right potential. So we have a Higgs potential with a mass term and a self-coupling terms, but what we have measured is only what happens very close to the minimum of this curve. So this potential could have another minimum, and so we could be in a metastable universe, and we could have some transition probability from this minimum to another minimum. And so what we can do is to expand the Higgs potential near the minimum, and we will get trilinear coupling terms and quartic coupling terms, giving rise, if you want, to final states where we have 2 Higgs boson or 3 Higgs boson, which are extremely rare and extremely difficult to study. And so these are what we have to look for to see, for example, if the Higgs boson gives mass to itself, if the self-coupling of the Higgs boson, which is measured by this number lambda. So we do that already at the LHC. For example, here, we see the best ways that we can do now. So we have, like, for example, we are looking for di-Higgs production in the final state. Like, here is an event that has 2 B jets. So we have 2 jets in the hadronic calorimeter. And on the other side, we have an hadronic tau and an electronic tau lepton. Or these other kind of events where we have 2 B jets and 2 photons in the electromagnetic calorimeter. So that's what we are doing now. And here is our maximal sensitivity at the moment with the data that we have collected in run 2 of the LHC. You can see here is the prediction of the standard model as a function of kappa lambda. When I say kappa, is also because I've always divided by the standard model. And so kappa lambda equal to 1 is the standard model itself. And you can see here what we measure experimentally. And so wherever the experimental measurements are below the theoretical curve, we have excluded that. So this is no longer allowed. And so you can see that at the moment, we have a kappa lambda that can be anywhere between -1 and 6.6 at 95% confidence level. And we still have a very blurred vision, but we have more improvements that can be implemented, and we will collect data until the end of 2025, and then we will have the ILUMI LHC. So, and this is our near future, okay? So here is a plan of the LHC. So we are in what is called run 3, and we are here in 2024. And we will run with the LHC until the end of 2025. Then we will have a big shutdown to refurbish our experiment in order to be able to take the amount of data that will be delivered by the high luminosity LHC. And so we will have a 2-fold increase in statistics by the end of run 3, and a 20-fold increase by the end of the ILUMI LHC, which is sort of telling you that we are still at the beginning of the LHC program. So what is the physics case of the ILUMI LHC in terms of the Higgs physics? Where we will do much better in this in the coupling of the Higgs to the various particles. We expect to have about 2 to 5% precision in most of the couplings. But if you can see here is a statistical, experimental, and the theoretical error. You can see that we start having that the red bar are almost bigger than our statistics and our experimental uncertainty. So more work is needed by the theorists in order to make these errors smaller if we want to get more from the data from the LHC. Also, in terms of HH, using BB tau tau and, for example, MBB gamma gamma, we have extrapolated the analysis that I showed you before. And you can see here that, for example, if we didn't have any error, we will already be able to, with the statistic of ILUMI with 3000 inverse Fantobar, you will have the sort of the black curve here. So you will be able to zoom in between 0.3 and 2.1, and the value of the standard model is kappa lambda equal to 1. Again, though, if you think that we can do better in terms of what are the errors that we have now, we will go between 0 and 2.7. But if we stay at the same levels that we are now, our image will not be much sharper. We will go only between -0.5 to 5.7. Again, though, we have also combination with the other experiment at the LHC, which is called the CMS, and we expect at least a value of 50% measurement on lambda, and this is still very conservative. I mean, machine learning, etc., has been very, very powerful for this. But many open questions remain. Why is the Higgs boson so light? What is the mechanism between electrosymmetry breaking? Why we have a free fermion family of fermions? And again, this question seems to be very linked to the Higgs boson through the Higgs couplings. Why do quark and charged leptons and neural leptons behave differently? And what is the origin of neutrino masses? Why is the universe matter dominated? Why is gravity so weak? And what is dark matter? And what is the dark energy causing the universe accelerated expansion? So the main problem is really that our, understanding remains very incomplete, and the standard model explains only 5% of the universe. So we really want to go beyond that. Nonetheless, the Higgs boson is very important to all of this question. For example, we know that protons are lighter than neutrons, and again, a lot of the protons and the neutron mass is due to electromagnetic and strong forces. But again, at the end, the proton is the protons are lighter because the up quark is lighter than the down quark, which is due in the standard model through the smaller coupling of the up quark with the Higgs boson with respect to the down quark. And again, the atom has a size because of the Bohr radius depend on the mass of the electron, and the mass of the electron depend on the coupling of the electron to the Higgs field. So, unfortunately, these coupling are very small, and so it will be very difficult to measure them experimentally. If we go again to the 2003 meetings, there is another reason why studying the Higgs boson is extremely important. The Higgs is a bridge to the vacuum. Breaking the vacuum symmetry is responsible for the masses of all elementary particles. This is closely related to the most unusual property of vacuum, dark energy, observed by astrophysicists. Again, there is a profound connection between particle physics, the very small and the very big. And it's the first time that we are studying a scalar particle similar to what could be the inflaton responsible to the very rapid expansion of the universe. And this was said by Lev Okun. Interesting also, Lev was commenting that R&D on click should be intensified, okay, which is quite interesting. So how do we go beyond the LHC and the luminosity LHC? We don't know the energy scale of the new physics, so we have to go there in two different ways. We can go there by direct searches, by increasing the mass scale, by increasing the energy, going to higher energy accelerator, or also by looking at smaller couplings. And in this respect, we can do it by more luminosity at the LHC, but also by building new machines that we are calling Higgs factory that allow us to look better, more precisely to the Higgs decays. And so we have this really twofold approach for looking at the future. So the future of an energy collider is quite complex, and there is a lot of focus on the Higgs boson. Here are the words that the two theories said about the Higgs. Every problem in the standard model originates from the Higgs interaction, was said by Jan Judice at CERN. And Nina Kani-Ahmed said, the Higgs is really new physics. Put it under the microscope, study it to death. And again, this is also what is the recommendation of looking at particle physics and at future of particle physics, is that one of our priorities should be to build first an electron-positron Higgs factory as an X collider. And the one at CERN is called FCC, the Future Circular Collider. But again, this machine will not do only Higgs physics. So the FCC will run between 90 and 350 GeV. So it will do precision Higgs, precision physics at the Z boson, the particles that were studied at LEP, and precision top measurement. And then we will have the FCCHH, which will reach 100 TeV, which will explore directly the energy frontier. And we also plan a machine that will bring electron and a proton interaction to understand the proton structure better in order to really exploit the FCCHH. So this is not the only idea that is on the table. There is also the idea that has been for a long time on the table. This is called the International Linear Collider, which will be a machine which will start around 240 GeV and then will be upgraded to up maybe to 1 TeV. We have CLIC that was mentioned already in 2003, which is using novel acceleration techniques based on high gradient room temperature RF cavities, which could reach 3 TeV. And then there is a program in China where you have an E plus E minus machine and a hadron followed by an hadron machine similar to what is proposed for the FCC. And there are also many new ideas emerging. There is a cool copper collider at SLAC, which could be then constructed at Fermilab. There is AF, and we have really one of the persons that has thought about this very nice idea, Brian Foster. We have colliders that we could use energy recovery LINAC in order to consume less energy for the future, which is very important, sustainability. And there are older ideas regaining momentum, like muon colliders. So, and some of these facilities, for example, in the case of ILC, the RF at DESY are almost a prototype for this machine. So this machine, if there was the money and the community there, they could be built actually quite fast. Again, this project have a very different readiness, but I just wanted to show you a little bit a square root of energy versus the number of Higgs boson. So the ILUMI LHC is here. So the ILUMI LHC will produce, you know, more Higgs bosons than, for example, the ILC, etc. But because you have collision of proton with proton, you don't have, you're not looking at this decay in a way that is very precise. It's very imprecise. And again, of course, FCCHH will produce 27,000 million Higgs boson. So it will be really a very different magnitude of scale. So what is the reach of this future collider? Well, here is the initial state of this future collider. And what you can see here, in gray you have, here you are looking at delta K over K in percentage. Okay, so your K is always your your coupling divided by the standard model coupling, okay? And in gray, you have the ILUMI LHC, which is already on, going to operate. And you can see here that by having, for example, the IS, this other machine, you will be able to measure the coupling of the Higgs to the charm. And so starting to explore the coupling of the Higgs with a second generation quarks. Again, in fact, the FCC will have a reach very close also to measure the coupling to the strange quark, which sounded almost impossible some time ago. And it might be close to measure also the coupling to the electron, which is very difficult, okay? And the final stage when you also have, you see, for example, here the muon collider. You can see, for example, the FCCHH here in dark blue. Obviously, if you put together the FCC with the FCCHH, the dark blue here, which is this complete program of CERN, it really gives you the best performance almost everywhere. You have a few places where the muon collider might be do a little bit better for H2WW, but it's really, I think that it's a winner. Why do we want to do that? We want to understand to disentangle the BSM. And for example, by measuring the Higgs coupling, we can have sort of a fingerprint to distinguish between different models. Here is, for example, the composite Higgs. Maybe the Higgs is not an elementary particle, or these are a kind of SUSY model, or if you just have an additional scalar. And you can see here that all of these models predict something different with respect to the standard model, okay? So for example, and you can see also that you need really a precision of about 1% in order to be able to distinguish these various models. Also, the future collider will be able really to look at this self-coupling, really looking at the shape of the Higgs potential. So you can see here, for example, the FCC and the muon colliders, they will reach a precision of a few percent in this quantity. And also, we will be able to explore SUSY, for example, in the direct searches up to 10 TeV. And again, as Jocelyn said, if you have SUSY, you will have a fantastic, one of the possible dark matter candidate. And again, this region is quite interesting. Again, this plot didn't come out very nicely, but here is the mass of the Higgs versus the mass of the stop quark. And you can see that the two plots, there should have been some other things here, I don't know what happened, but they cross at about 10 TeV. So 10 TeV seems to be quite an interesting area. So where do we stand? So we have done in 2019, we have done a conceptual study of FCC, and this was followed by feasibility study, and which is going on right now, and it will finish in 2025. And the feasibility study is going to study the geology, is going to optimize the ring placement, is going to optimize the design, is going to identify the R&D that you have to do in order to decrease the cost of this amazing machine, and identify the resources. The midterm review was just presented recently at the CERN Council, and that's why there was an article on the BBC media that you might have seen in February. So here is the description of the optimized placement. So the circumference is 90.7 kilometers, and there are going to be 8 surface sites that have been decided. And so you might have up to 4 experiments focusing on different aspects of the physics that can be provided by the LHC, by the FCC. Like, for example, one focusing on Higgs, one could be focused on the physics at the Z boson, one could be focused on long-lived particles. So there could be a lot of different physics that you could explore. And again, for example, CERN has already started to speak with every village around this map in order to get the political consensus. And it's not only to get the political consensus, you also have to identify if there are roads, if there is power, if there is water, and all of these have been done and trying, to go to the detail of this process. So what is a timeline? The timeline is a bit scary, okay? So if the FCC could start now, especially the FCCE, we have the technology, and so we could have physics operation in around 2040, okay, or perhaps even earlier. But we are still doing the ILUMI LHC, so we cannot start now. We don't have the money yet, and so we will have to wait And for the first stage, we hope to be in operation in 2048 to, it's about here, 2045 to 2048 until 2063. And then going to the FCCHH, the proton-proton, and this time will be used to do a lot of R&D in order to really to get these magnets that we will need for reaching this energy. And so the operation will be even later. So again, though, these are amazing projects. They will need a lot of R&D to get us there. And you need R&D that we have done actually for ILC. We have, we have demonstrated that we could have nanobeams of the level of 7.7 nanometer in order to have the luminosity reach that is needed at a linear collider. We are trying to get a better superconductive RF in order to decrease the cost of these facilities. We are doing now R&D for the FCCHH to build 16 Tesla magnet to have this 100 TV beam. And again, we are looking both at moving from niobium tin, like the magnets that are now reaching 8 Tesla at the LHC, to go to niobium-free tin. And again, as you can see here, we have already small demonstrator. But again, it's really difficult to go from a small demonstrator to do a ring, because you really have to decrease the cost. You have to industrialize the process. And again, we are also looking at the superconductor, low temperature superconductor, high temperature superconductor. Like for example, in China, they are looking at iron-based high temperature superconductor, and at CERN we are looking at REFCO. You need innovation for the detectors. Like for example, for the detector at an E+ E- machine, the detectors are not huge, but you will have to build, if you want to measure the coupling of the Higgs to charm, you will have to achieve a resolution of about 1 to 5 micron, which means that you will have to have very low material in this detector and dissipate very low power. And again, you will have also to build excellent calorimeter and compact calorimeter. And again, there is a lot of work that is already ongoing here. For example, there is a detector that is planned for the ALICE detector at CERN, where you are using very, very, very thin silicon so that you can bend it. And there is a detector that we are building here in Oxford for mu3e, where we are providing carbon fiber support, which is only 25 microns thin. Very impressive. And again, for FCCHH, we will have huge detector, so we will have to build very large cavern. We will have, again, a very big silicon tracker. We will have enormous radiation level at the order of 10 to the 18 neutron equivalent per centimeter square. We will have to have a very high magnetic field to bend these tracks, and it will be very complex. But again, we are doing R&D to try to see how silicon is behaving at very high doses. And we have good news. At the moment, we thought that the silicon was becoming sort of worse linearly as a function of the dose. And in fact, now we are seeing with our measurements that in fact is sort of saturating. So we have some hope that silicon will survive also that. We need innovation in computing and analysis. Machine learning is a common thread with everything we do. For example, here is an atlas to distinguish a jet that is coming from a big quark or a C quark or a light quark. We have to measure very precisely, the displacement of the vertex from the origin. And again, we are doing this better and better using machine learning. For example, using the graph neural network, we have obtained a light rejection factor of 1,000. So every time we see, by using state-of-the-art machine learning, we are doing much better than we expected. And again, by doing that, we are also training a community and young people in things that are very useful for society. So in conclusion, finding the Higgs boson has completed the standard model, but many questions remain unanswered. Precision study of the Higgs and going beyond the standard model will require new accelerator. The cost is significant. I didn't mention the cost, but it's really large. But the physics output is superb, and we will use this machine for decades. Timelines are very challenging, though, for student training and career, because it's so long, the time scale. We will need to be extremely innovative to make the next step, and this will have a tremendous societal impact. Progress in fundamental physics will be made, as we have seen today, with accelerator, and I spoke about that, neutrinos, like Mark and Paul said, by doing very broad searches from dark matter, as illustrated by Jocelyn, but also by astrophysics experiment measuring dark energy and dark matter. And really here, I want to go back to Don, and to finish with what Don said in 2003.
They've gone into this field because they feel that the big challenges are there. And it's a very rapidly moving field, astrophysics. It's going a lot faster ahead with time, starting a long way backwards, but it's going faster ahead in time than is particle physics. So it's something that one should bear in mind for the very distant future. And actually, I don't know how many people here have read the CERN Convention. I know it's 50 years old, but it's never been abrogated, and it states very clearly what the duties of the CERN laboratory are. It's made a long list, and the study of cosmic particles appears not once but twice in that list. So we're cleared to do it if we want to do it.
So again, as you say, he was really very strongly pushing for astrophysics experiments. Thank you, and I hope that I didn't go beyond. No, not too bad.